In this video, we're going to perform an exponential regression using technology, a TI-84 plus in this case, and we are going to interpret the r-squared value of that regression and then use the regression for interpolation and extrapolation. So before we do that, let's refresh ourselves on what a scatter plot looks like. So recall that a scatter plot is just a graph that we form from two pairs of numerical data, and it's treated as if there's some sort of link between them. So here what we see is the time and temperature for a cup of coffee that's just been left sitting on somebody's desk. So at time 0, when we first start watching this cup of coffee, it's at 179.5 degrees, and then we see this coffee cooling off as time progresses, and after 50 minutes it's down to a temperature of 100.5. So we can see that there is, in fact, some sort of relationship between these two variables, and that's what we use a scatter plot for. We're looking for that relationship between those two sets of data. Now, the way we've done this before is by finding what's called a linear regression. So that linear regression finds a line called the line of best fit, and we describe that line using an equation, and we run that through the data. So you can see our line kind of in purple that we have put over this, and we can describe that with an equation in the form y equals mx plus b, where m is the slope, b is the y-intercept, and we can use this, and this is pretty important, to make predictions. For example, if I were to look at this and ask, what is the temperature, let's say, and let's pick something we definitely don't have here. What's the temperature after 40 minutes? And we can see that we don't have 40 in our chart, so we don't have that information readily available. What we can do, though, is on our graph, start at 40 minutes on the x-axis. We can see that point would be right there on my line of best fit, and I can run that over, and I see that that would be somewhere in the neighborhood of, looks like just under 110. We are estimating there. But that makes sense if we look at it here. It should be somewhere around 110, and we can see that that is the case. So I can use this line to make predictions about data that I don't have. So here I would say probably about 107 or so degrees Fahrenheit. And these predictions are simply as good as my regression. And remember, we would look at the correlation coefficient, R, to tell how good our regression is. So if we were to look at R for this particular line through this data, we would see that it's not bad, but it's not great either. And the reason why is that our data is simply not linear. We need a different kind of regression. This shape, if you'll look here, and there'll be a better line on the next slide, but if we just kind of trace in our mind what this data is doing, and if we do it in a way that is not just a terrible drawing, way to go, Mr. Kelly, you can see that it's kind of this banana curve that we almost have come to expect out of an exponential. And in fact, this data is exponential. And so what we need is called an exponential regression. So we would fit a curve, not a straight line, to this data. So what we're going to do now is we're going to look at exactly how to do that. So here is our example, very similar to the one we were looking at there. We've got a cup of soup, we leave it on the countertop to cool, and we can see the temperature of the soup after a certain number of minutes. And what we want to do is write an exponential regression for this, rounding to the nearest thousandths place, that will tell us or give us the ability to predict the temperature if we know the time. So what we need to do here is go to our handy dandy TI-84, and we're going to go through the steps of making an exponential regression. Now, these steps are at the bottom of your notes page, so don't feel like you have to write them down as we go. I just want you to see how to do this. Those notes are at the bottom of your notes, rather, the section that is in a dotted line. I kind of expect you to cut out and to keep next to you as sort of a study guide for how to do this. So step one, what we're going to do is we are going to turn on the diagnostics so that we can see the correlation coefficient, r squared in this case. So what we're going to do is we press the second button and then catalog, so that's 0, second 0, and this brings up everything that's there. And we want to find the instruction diagnostic on. Now I can scroll through all of these, or if I just see where the green D is right there, if I hit that, it'll take me right to the D's, and I am looking for diagnostic on. So now I'm going to hit enter once and then enter again, and I've now turned that on. So the next thing I need to do is I need to enter this data into the calculator. So this data right here has to actually go into the calculator. In order to do that, I'm going to go to the stat menu, and I want to edit my list, so I just hit stat and then enter. And now I put all the X values, so the minutes in this case, in L1, and all the Y values in L2. Once you have typed in all the data, make sure it matches everything that you have in your chart, so check it over again so that you don't just make a careless error. Also, make sure that your lists are of the same length, otherwise your calculator will give you an error called a dimension mismatch. And if you see that, that just means you have one more in one list or the other, or two more or three more. They don't line up, they don't have the same number. Alright, once I have all the data entered into the calculator, the next thing that I'm going to do is to select now an exponential regression. Now before we would choose a linear regression, but our data is not linear now, it's exponential. So what I'm going to do is I'm going to go to Stat, Calculate, so that's over here, so I just hit my right arrow, and I want to find an exponential regression. Now before we use this one, but again, this isn't linear, this is exponential, so I just keep scrolling down, and option 0 is exponential regression. I'm going to hit enter, and then enter one more time, and it's going to bring up this data. Now on your particular calculator, it may bring up a menu in between this, and it'll ask you to use the down arrow and go to where it says calculate at the bottom, and then hit enter, and then it will give you this screen. But now this is our result. We were asked for an exponential regression equation, and here it is. So when writing this out, you won't necessarily have to write this part, but I'm writing it down to show you what all this means. We're having an exponential equation of the form y equals a times b raised to the x, and this menu over here just tells you what a and b are. So a, our initial value, our y-intercept, is 180.377. Notice I'm rounding off to the thousandths place, so that's 3 places past the decimal point. 8 is bigger than 5, so I rounded that up. Times b, which is 0.954, again rounding off to the thousandths place, raised to the x power. Now let's bring some common sense to this game. I know that this temperature is going down. This is exponential decay, so I would expect my growth factor to be less than 1. And hey, look, 0.954 is less than 1. So I do have exponential decay here. And I can pretty cleanly see that this makes sense with the data, that our y-intercept would be about 180. Hey, that's what it is in our data. So this looks like it would be a pretty good fit. So here's how I can tell whether or not this is a pretty good fit. I look at the correlation coefficient r squared. Now, in a linear regression, we were looking at r, but anytime we have a curve rather than a line, we always want to look at r squared. And notice up here it gives us r squared and r. R squared is not going to have a sign. It's always going to be positive. And it just gives us some idea of the, if you want to think about this, or think about it this way, the distance of each point away from that curve. And we don't care if it's above or below. We just want it to be as close as possible. And in fact, the closer the r-squared value is to 1, the better the fit of the regression. So in this case, my r-squared value, my pen would work. Oh, there it goes. It works all at the same time. Isn't that lovely? My r-squared value is 0.987. That is very close to 1, so we can see that this is a very good fit for our data. So any prediction that we make with this equation is going to be fairly reliable. And recall that that's a big part of the point of these regressions is to make those predictions. So let's make some predictions. Predict the temperature of the soup after 5 minutes and then 15 minutes. And you'll notice neither 5 nor 15 is in our data, so we are making predictions that are not included in our data. So we start with our equation, y equals 180.377 times, and then my growth factor, 0.954, raised to the x. Now notice that x is the time in minutes. So if I want to know what's going on here after 5 minutes, all I have to do is replace the x in that equation, which remember is an exponent, with 5. And thankfully we have this handy dandy calculator that will allow us to enter that data in. So I'm going to clear out my regression equation, and I'm just going to type this straight into the calculator. There is no reason for me to try and do this in my head or on paper. It is too much. Remember that when you are entering in an exponent, use the caret above the division symbol, and we want this raised to the 5th power. And if we hit enter, we are given a value, and so that value is 142.535. If you are not given explicit instructions on rounding, just round off to what everything else is rounded off to. So here we're all rounded off to the thousandths place, so we'll round this to the thousandths place as well. So after 5 minutes, we would expect the temperature to be about 142 degrees. Now let's check and see if that makes sense. At 4 minutes, it was 146. At 6 minutes, it was 135. Well, that seems to make a lot of sense that after 5 minutes, it would be about 142 degrees. So now we can repeat this for 15, and now 15 is outside of the data that we have. So we'll not really have a way to check this, and it is really moving outside of anything that we have our experience. So we're assuming this is going to keep cooling off the same way, and if it does, well, the calculator can tell us what's going on there. Let me show you a trick. Rather than type in all of this again, if I press second enter, it'll bring up the last thing I typed, but give me the option to edit it. So I can just change that 5 to a 15. And when I do, I find that my regression equation predicts the temperature should be 89.003. And we can, as best we can, see if that makes sense. We see after 10 minutes it was 110 degrees. So it is cooling off, and we can see that this would continue a trend of cooling off, so that seems to make sense. We can also realize that this is an application of what's called Newton's law of cooling, which says that the temperature, or the change in temperature rather, is going to be related to the difference between the temperature and room temperature, and that this thing is eventually going to come to room temperature. So after 15 minutes, we're getting closer to what the average room would be, which would be about 70 degrees Fahrenheit. Now, if you look at the bottom of your notes page, you have instructions step by step for how to get to the exponential regression in your TI-84. Now, I would really dearly love for you to use this as you practice, but make sure that you are using it with the thought of getting good at it now and setting it aside later. We want to eventually get to the point where this knowledge is in your head, because you will not be allowed to use this on the quiz. Happy practice and good luck.